on the clock. So, welcome back to the lecture 10, and today we will follow the previous discussion that we had, and we will solve a couple of examples for to find potential and from potential electric field and maybe charge densities in space for dielectric material. So last time, what we have done, we understood that the problems that we are going to tackle is a little bit difficult because we are talking about macroscopic system, and we go to the macroscopic system. Indeed, we must go to. We are talking about, let's say, 10 power of 18 to power of 20 of atoms or molecules, which they are essentially distributed in space, and then going from macroscopic scale to macroscopic scale is needed. And that was what we performed, and we did an approximation in a coordinate which, let's say, the charge distribution around the atoms or molecule is given. And we only kept the first approximation, which was a dipole approximation, and at the end of the day, we came up with an electric field. So that was what we had. So we had so many of those samples, and then we moved from continuous space to the discrete space to the continuous space, and position for each of them was given, and we look at the finding the potential at any given place of X. So I remember at that time I used the Xi, and then here was X prime. But later on we changed the notation, and I say that, hey guys, be careful that X prime that I do have in mathematics is a little bit different from what we define. So anyway, I will erase the notation just in order to not get you further, give you further confusion. So we find the electric field to be given at the point of X by 1 divided by 4 pi epsilon 0. And then we had the charge distribution, which was given in the space d3 of X prime divided by X minus X prime. And from the approximation that we had another contribution, which was 1 divided by 4 pi epsilon 0 integral of, if I'm not wrong, we had P of X prime dot. There is something missing, which I will correct it later on. 1 divided by X minus X prime. Excuse me. D3 of X prime. Remember that was electric field, so indeed we had the electric field at the point of X was given by minus gradient of this quantity. Okay, so this is what we had from the previous calculation, and essentially the first term is what we are expecting for specific charge distribution in the space. Okay, and you know that we did the ensemble. We moved from one molecule to the, let's say, many molecules in a given volume of V, which is here. And then we got this expression. So the first term, as we described, that is describing the situation for a net charge density of rho of X prime, while the second one is given by a term which is, if you remember, we call it polarization, or we call it dipole moment densities. Okay, which was the number of dipole moments per volume, essentially. Okay, so then we did a little bit of mathematics. We did a calculation and find that the divergence of E, and if you could take the derivative, the divergence of the above expression, doing a little bit of mathematics, we get the following expression. which from the first term we got rho divided by epsilon 0, and from the second term we got minus divergence of P. Okay, and remember that how did we get this? It was divergence of a gradient was Laplacian, and Laplacian of 1 divided by x minus x prime was 4 pi delta of x minus x prime, and for the other one also it was the same situation. And however, for the second term, you have to do also a by-part integral, integral by part, which means that you have to bring it to the surface and then solving the expression. And from this expression, what we got the divergence of E multiplied by epsilon 0 plus P is equal to 0. So remember, if we had vacuum, for vacuum, we had divergence of E multiplied by epsilon 0 was rho, while if we have material with certain polarization density, then it seems that that polarization density needed to be added to the electric field somehow to give you the charge density in the space. Okay, and we say that this expression, essentially epsilon 0 plus E plus P, we call it another vector, which is very important, which call it displacement vector, or electric field displacement vector. And then we write Gauss law for material as divergence of D equal to rho. Okay? That's a definition, by the way. Maybe it was one of those wrong definitions because, you know, displacement is already used in physics in different area. Even I don't like this one, polarization, because polarization is already used in many different areas. So at the beginning of electromagnetic fields, people, they were not very careful to not repeating the names. So we have so many names like polarization. So I'm sure that you are familiar with that, or displacement, which we use it in dynamics, classical dynamics as well. Beautiful. So in the big picture, what is happening if you assume that you have a material in a space, which is, let's go with our previous discussion that we had. We assume that we have a cube of 1 millimeter by 1 millimeter by 1 millimeter of a specific material. And it seems that, excuse me, it seems that if you place a specific charge distribution inside of that, which is a charge distribution of rho inside of this material, then electric field at any given place here is given by specific expression. So which means that the divergence of epsilon 0 E plus P is equal to rho. And you have to solve this equation. Nevertheless, for electrostatic, always we do have the curl of E equal to 0. Okay, so now we have two expressions. The first one, which was the Gauss law, is now modified, and the modification is given by the polarization density, which is the material property that you have to consider it. And the second equation that you needed is the curl of E, which is equal to 0 for the case of electrostatic. For the case of non-electrostatic, that is given by the derivative of magnetic field in time. Okay, so we are not talking about that scenario. So that's the point. So that's the point. So you have to really solve these equations and understanding what's going on there. So it seems that when you have vacuum, and when you have material, the electric field in space is changing. And that's reasonable, because if you look at the atoms, even if you assume the neutral atoms, then you have a nucleus, and then you have a cloud of electrons around it, okay? The total charge is 0, right? For a neutral atom. True? However, if you place this neutral atom in the presence of an electric field, which means that if you place a charge somewhere, then you are creating electric field in a space. And then if you have atoms around these, let's say, point charges, what is happening that the distribution of the cloud, which usually I prefer electron to be blue and proton to be red, this distribution is perturbed by the electric field. So it means that you don't see the center of the charges to be perfectly superimposed. So what is happening, then the charge, the plus charge will be here, and the cloud will be a little bit affected. Remember that usually we know that the force that we do have and the displacement, and the force is identical essentially, and both of them, but the mass of proton is way, way higher than the mass of electron. So very likely electron will be perturbed further and not the proton, okay? So it means that if you apply the forces, the one with the higher inertia, which is higher mass inertia, will be less displaced with respect to the other one, okay? Is that clear? So the cloud of electron on the other side is changed. So the center for the positive charge is here. Is here, while the center for the negative charge is here. So then you have a dipole moment here, which is it's from negative to positive, yes, dipole moment. So you do have a P. And you do have so many of them around it. And these P, essentially, they are producing electric field which interfere with the electric field due to the point charges that you place it in a space. And they are changing the total electric field in a space. So that's the reason that we developed the above theory and the previous theory, and we got the following expression. So then it means that we are no longer allowed to use divergence of E equal to 0, equal to rho divided by epsilon 0 for materials. Okay? Perfect. So can you tell me, guys, what happens if the electric field here is increasing? So if I increase the electric field, what do you expect for the P? Don't be shy, just tell me.
Should be more polarized.
Will be more polar, yes, of course it will be more polarized. So indeed, P, which I do have it here, and right now, remember, I'm talking about a single atom, but we can talk about polarization density, which is dipole moment density, which is the all of the dipole moments in a volume. This P, with applying the electric field, will increase, right? So it means that the P essentially is a function of E, all right? So if you apply the electric field, then the P also will change. And this, there is a specific functionality here. Now we consider specific situations. The first situation is that, excuse me, whenever you apply the electric field, the dipole moment will increase proportional to the electric field. Okay, what does it mean? That P is proportional to the electric field. Okay, or we call this linear regime. We assume that the polarization has a one-to-one response to the electric field. If you increase the magnitude by 1, then the polarization also will change by 1. Okay, we make that, we don't like to go with proportionality. Usually we make it equal, so we go with P equal to epsilon 0 chi E. And usually we call these chi electric, which is the electric. Usually I'm not so good with names, guys. They call it electric susceptibility. All right. The other case is that, excuse me, P is not only function of E, but also is a function of E squared, or function of E power of 3, or function of E power of 4, and etc. So then P, I will go directly with this case, which is epsilon 0. I will take it out. And now I'm using a different notation. Definitely, P has 3 components because it's a vector, right? It's a polarization. It can be a vector in a space. It's a 3-dimensional vector. So I can talk about the I's component of that. Then it can be depending on chi I, j, e, j, which is the linear term. Don't get surprised. This is exactly identical to what we had it here. Is the same term. And the other term is chi I, j, k, e, j, e, k. So it means that the electric field, after certain values, that term plays role and is significant. And what is happening that by applying electric field, you will see that the response of the polarization will be way stronger. And it doesn't go with power of E, but it goes with power of 2 of E. So it will be E squared or E power of 3. So that's the other one, which is chi I, j, k, l, E, j, e, k, e, l, plus the other 2. Okay.
Excuse me. In the second term, it's EJ, EK, right?
Yes, thank you very much. Yes, indeed. EJ, EK. Thank you.
Sorry, Dr. Karimi.
Yes.
So when we say chi ijk, this means that chi has dependent both on the direction of P and E.
Chi, yes. Yeah. I will tell you further. Yes, I will tell you more about that. Because P is not, look, P is a response. So you cannot say that it's depending on the direction of P. Right? P is the response of material to the external electric field. So let me finish the notation. So usually we put a label of this just to understand which level we are considering. So that's the electric susceptibility of order 1, order 2, order 3, which is associated to being in the linear regime, nonlinear regime, or nonlinear regime of power of 3. Okay? They call it Chi2 material, Chi3 material. This is the definition that you can see it in, for example, in the course of Bob Boyd, which is a legend in the nonlinear optics. Okay? So, and I am sure that you have taken that course, or some of you may not, but you should take this course. It's a great opportunity. And if you look at, if you pay attention to some of Bob's presentation, usually he writes this equation and say that the entire my book is about that. And then just spelling out all of the properties of this material and talking about chi's. Okay, fantastic. So now, let's come back to this equation. By the way, I can go and talk about this expression, but I would prefer to talk about what we do have for the general case. Is that fine? Good. Okay. So the first case, remember that chi1, chi2, and chi3, etc. Usually, if you go to higher level chi-n is usually smaller than the other term. Okay? So the higher terms, usually they are way smaller than the first terms. Some of them may not exist. Okay? So some of them they may exist for specific materials. For example, depending on the symmetry, you may have specific chi's and not the others. Okay, for example, for atoms, you may have specific property, and due to the symmetry that you do have, some of those chi's they disappear. All right. Only the odd terms, they will remain. The even term does not exist. So you have to pay attention to the property of material and understanding what's going on with those chi's. In general, chi's are tensors. I, J, until I don't know, M, and N, they are tensors of rank, specific rank. So let's assume the first approximation, which means that within the first approximation, Pi is given by epsilon 0, chi1 of ij, ej. Excuse me. So let's follow the Melika's question. Melika asked, what is happening with the chi's for different materials? Let's go for this specific case, which is Px is given by epsilon 0 chi1 of xx ex plus chi1 of xy ey plus chi xz of 1 of ez, and etc. Okay, so essentially px, py, pz, they are given by epsilon 0 chi xx, chi xy, chi xz, chi yx, yy, chi yz, chi zx, chi zy, chi zz of Ex, Ey. Remember, all of them, they are chi1. All right. So it seems that, surprisingly, if I assume, in principle, even if I have the electric field along Z, there is a possibility that the material responds such a way that you have a polarization along X. This is what you will get it from this expression. Which is surprising, maybe to you. We may have materials, which these materials, they have strange reaction to the electric field. If you apply the electric field in that direction, then you will see that the dipole moment appears in that direction. Okay? Is that clear? Perfect. So indeed, that chi, which we describe as a tensor of rank 2, by the way, this is a rank 2 tensor, is a general first order approximation that you have, or first response to the electric field. Okay? And in general, if you have a response which is given by these, let's say, chi's, we call them in general that material biaxial material. Okay? We can discuss about that, because I'm sure that the name is familiar to you. You heard of that. Well, if you do have the property in such a way that only two directions are identical and one direction is different, then we call it uniaxial. And for all of them, we call them birefringent material. Okay. It may happen, in general, it may happen that the off-diagonal term are 0. So chi x, y, or let me write it in general way, chi ij for I not equal to j is 0. And all other terms, which is chi 1, 1, chi 2, 2, chi 3, 3, they are equal to the same value. Then P in that specific case is given by epsilon 0, chi E, which is what we call it isotropic material. Like a glass, for example, is isotropic material. Okay? Within first approximation, also air is isotropic. I'm not talking about really high energy electric and magnetic field, which even can ionize it, and then you may have some other properties for noble gases there. Okay? And moreover, chi E can be a function of coordinates. So in what I mean that chi E can be a function of x. In general, it can be, okay? But now I don't consider that. We call it homogeneous material. When here, the chi is identical, we call this material homogeneous material. So let's revisit the equation that we had. D was given by epsilon 0 E plus P. And for homogeneous isotropic material, that was given by epsilon 0 chi E E. Then you can factor it out. You will get epsilon 0, 1 plus chi E. All right. And this term, which means that, so the entire of this, let's call it epsilon E, which means that it seems that the electric field, the displacement vector for vacuum, which essentially is given by epsilon 0 E, this for vacuum. For this isotropic homogeneous material is given by epsilon E, which epsilon is equal to epsilon 0, 1 plus chi E. Or epsilon divided by epsilon 0 is 1 plus chi E. We call it dielectric constant. Excuse me, guys. And that one also they call it electric permittivity. Good. From this, we will see it in next two lectures. We can define refractive index, which is n, or essentially n squared here. All right. Beautiful. So just learn and digest these properties of material. And then, of course, in general, D is given by epsilon 0 E plus P, which is epsilon 0 chi. Now let's write it in this form. Ij. Well, let's write it in a formal way. Ej plus chi 2 ijk ej ek plus the other term. And epsilon 0 can be factored out. Then what you will have 1 plus chi ij ej plus chi I 2 jk ej ek plus that. Okay. We usually, in this course of electrodynamics, we usually do not consider the nonlinear term. So we are not considering these terms. These are very important. If you go to nonlinear optics or ultra-fast optics, they play a significant role. However, we stay with this expression, which is D is given by epsilon E plus epsilon 0 E epsilon 0 chi E of, sorry, let's go with this way, di is given by epsilon 0 delta of ij plus chi I j1 ej, which means that the only term that will be added to the calculation that you had is is an identity matrix which with an epsilon 0 at the front of it. Okay, so that will be essentially nothing more than epsilon 0 with identity matrix plus what you had it as a chi ij in your calculation. Okay, that comes from the first term. And that's the source for birefringence. So let's say the birefringence material. So you do have different response and different displacement vector for applying electric field in different directions. All right, so I think it's very clear now for us that even if you assume a material like this and you apply an electric field here, very likely you will have a polarization inside of the material. You may have a polarization inside of the material. I want to be careful with plotting this. And this polarization not necessarily is along the electric field that you apply. It can be changed in the space. Even it cannot be in that space, that direction. It can be even along this specific direction, which is P. Good. And how you can calculate the P? With the chi, with the material property that we already discussed and we assume. Good. Now the question that we have is that what is happening essentially when the material doesn't have a net charge? So this material doesn't have a net charge, does not possess a net charge. Then what is going on with the potential? Do you remember that electric field was given by minus gradient of an expression, which was given at the beginning of the lecture? I'm talking about that expression. 1 divided by 4 pi, the charge density, and then you have another term which is given by P dot the gradient of 1 divided by x minus x prime. Okay, so here the same situation will happen. So essentially phi that we had for at any given place of x was 1 divided by 4 pi epsilon 0 integral of rho of x prime x minus x prime d3 of x prime. And then we had another term which was 1 divided by 4 pi epsilon 0 integral of p of x prime dot gradient of 1 divided by x minus x prime d3 of x prime. That was on volume 3. And we assume that we don't have the charge distribution, charge density. Then the only term that plays role is the last term in our potential. So for that specific situation, we do have potential at x is given by 1 divided by 4 pi epsilon 0 integral of p of x prime dot gradient of 1 divided by x minus x prime d3 of x prime. Do you agree? That's over the volume that we are considering, which is explicitly that volume that we do have. All right, and now we want to understand what is the contribution of these polarization in the potential, because previously we understood that the net charge plays role. And now what we see that it seems that polarization, that gradient of something will play a role as well. And we want to understand what are those actions and what is happening with the polarization density that plays role in calculating our potential. So let's do a little bit of bipartite integral. So in order to do so, I will calculate what is going on with the divergence of P. Let's go with the divergence of a vector F times a scalar G. So divergence, as we know, it's just derivative with respect to I of F, or let's remove also the gradient and the prime just for simplicity, of Fi G, then that is G derivative of Fi plus Fi derivative of G. Do you agree? And this simply means that is G divergence of F plus F dot gradient of G. Now I will do this expression. So I will do the calculation of gradient, the gradient divergence of P of X prime to X minus X prime. That will be 1 divided by X minus X prime. That is the scalar quantity, divergence of P X prime plus excuse me, P of X prime dot gradient of 1 divided by X minus X prime. Are we good? What we do have in the integral, we do have this term. So then I will take the first term, which is that one, to the second, to the left side. Then the expression will be given by P of X prime or dot gradient of 1 divided by X minus X prime is equal to divergence with respect to prime index of X prime divided by X minus X prime minus 1 divided by X minus X prime divergence of P of X prime. Good. Substituting inside of the potential, then we get 1 divided by 4 pi epsilon 0 integral of two terms, divergence with respect to prime index of P of X prime divided by X minus X prime minus, or let's write it as a plus, minus divergence of P of X prime with respect to prime index X minus X prime d3 of X prime. Good. Perfect. And that's on the volume V, which is the material that we do have, or we consider. So what is happening with the first term? Can I use the Gauss theorem? Bring it from volume to the surface? Because that's a divergence, right? So that will be 1 divided by 4 pi epsilon 0 integral of P of X prime dot n prime d2 of X prime divided by X minus X prime. And that's on the surface. plus 1 divided by 4 pi epsilon 0 integral of minus divergence with respect to prime of p of x prime, x minus x prime, d3 of x prime. That's on the volume of V. What is your feeling about this expression? This is look like what? Let me write down something else for you. In general, if you remember that we had the potential, if we had the charge distribution on a surface, we had 1 divided by 4 pi epsilon 0 integral of sigma of x prime d2 of x prime, x minus x prime, and that was on the surface. If we had the charge distribution in a volume, we have another contribution, which is 1 divided by 4 pi epsilon 0 integral of rho of x prime d3 of x prime divided by x minus x prime on a volume. Comparing these two forms with the above expression here, it brings us to a conclusion that these look like a charge density on the surface, because that's an integral on the surface, and that one is look like a charge density on a volume. Do you agree, guys? So it seems that if you have a polarization or dipole moment density for a material, you do have two contributions. One is, it seems that you have some sort of charge density inside the material. And the other one is that on the surface, it seems that the charge density on the surface will appear. So both of them, they play a role in order to change your electric field or the potential outside of that surface, okay? Or outside of that volume. So indeed, then it seemed that the phi of x that we have two terms. One of them is phi of x due to the sigma or due to the p dot n, and the other one is due to the rho, which is minus, pay attention, divergence of p. So you do have two contributions now. One due to the volume charge distribution, and the other one due to the surface charge distribution. Let's see. Let's see intuitively what is happening. Assuming that I have a material like this, assume that it is perfectly isotropic, right? Which means that it doesn't matter where the electric field direction is, always the polarization is along that direction. So if that's the electric field, what is happening with this material? P appears. The negative charges, they will come here. And the positive charge, they will go here. Do you agree? Then the direction of the polarization will be along this. Do you agree that P is a constant, is not functional position? Because we assume that the electric field is perfectly uniform, and this material also responds in a linear way to the electric field and not function of the position. So P is a constant inside of material. Right? I'm not talking about outside because there is jump. So what is going on with the divergence of P? Is 0. So definitely due to the volume, there is no contribution to the electric field. Okay? Volume charge distribution will be uniform there, so nothing happens. The only effect that happens is on the surface. What is happening with P at the surface? P dot n will be the dipole moment dot the n, so it will, here it's negative, while here is a positive. So what happens essentially, that P dot n will give you two charge distributions. So if the total charges that they are moving to the surface is Q, then here the charge distribution will be minus Q divided by A, which is that surface that you have. And here Q will be, sigma will be Q divided by A. So it seems that due to the electric field, which previously this material was completely neutral and having no net charges, but due to the electric field that you apply, still inside of the volume, there is no net charge, but due to the electric field and polarization that happens there, due to the dipole moment, on the surface close to the side that the electric field is created, negative charge will appear, and far from these, the positive charge will appear. So these two, they will play a role, and they will change what's going on with the electric field inside of this material. All right? So indeed, inside of this material, what we have, we have E0 plus P, which is given by, I don't know, D of N. So inside of this material, if you can do the mathematics, you will understand what's going on with the electric field. And that will be the subject of our discussion for the next next 1 hour and 30 minutes, only going through these calculations, finding that for specific material, what's going on with the electric field inside. Do you get that? It may happen either due to the form of electric field or due to the material property that even divergence of P is not 0. Then what happens, that it seems that due to the electric field that you apply and the property of the material, certain charge distribution will happen at the center or inside of the material, which also they play a role in changing the potential outside or inside of the material. Is that clear? Beautiful. So now with this, I will go and revise the boundary conditions that we had, and we will solve the problem for a couple of boundary conditions. So first of all, here we deal with displacement vector or electric field displacement vector, which is D, which is given by rho. And also we have curl of E for electrostatic, which is 0. Now, assuming that I have two materials with a specific boundary condition, which is, I don't know, right? This is material number 1 and material number 2. And I assume that the normal to the surface is given here. Then I can use the gauge law, and assuming that I have a small cylinder here, and writing the gauge law for here, so which means that integral of divergence of D is D3x is equal to integral of rho D3 of x. And if you do the mathematics, which what we have done previously, assuming that also epsilon 1 and epsilon 2, they are not coordinate dependent, because if they are coordinate dependent, that will be a little bit of challenging for us. we will get the following expression, which means that epsilon1, oh, let's go with this way. First, let's go with the displacement vector. D2 minus D1 dot n is equal to sigma, or what we call it D2n minus D1n is equal to sigma. If you remember previously for vacuum, what we had E2n minus E1n was given by sigma divided by epsilon 0. Now, when we are talking about material, is that clear, or should I drive that equation? I think it's clear, right? So it's simple enough. For the curl of E, which is exactly the same that we had for vacuum, we obtained that E to 2t is equal to E1t. The tangent of the electric field is identical. Okay, exactly similar to what we had it for vacuum. Or people, they write it out, even sometimes they write it as a E2 minus E1 cross n is equal to 0, but it's the same essentially. It's a tangent component of the electric field, which is continuous. Okay, so remember what we discussed previously for the electric field normal vector or normal component is true for normal of the displacement vector. Clear? So there is a jump or discontinuity in the normal of displacement vector whenever you have a charge density, surface charge density, which was very similar to what we have it for electric field in vacuum. Good? So the only changes is that here now we are dealing with D2n minus D1n equal to the charge density on the surface. And remember, for material, as I say, that it's different for birefringent material, but so far we assume that the material is homogeneous and isotropic. So then, I mean, in that region is isotropic, of course. It's homogeneous, is isotropic, but not homogeneous. So then what is happening that epsilon 2 E2n minus epsilon 1 E1n is equal to sigma. Okay, I assume that epsilon 2 and epsilon 1, they are scalar quantities. If it's getting to be birefringent, that equation will be a little bit needs to be handled a little bit carefully. Okay. Do you have any questions? No? Okay, so let's have a break of 15 minutes, and then we will see each other and we will solve a couple of questions and examples. I will stop the recording. Perfect. So now that we learn about material and what's going on with the electric field, let's solve a couple of problems, a couple of physical problems. Assume that we have a material with dielectric constant of epsilon 1. So this material is almost everywhere. Okay. Now the question is, what's going on with electric fields or potential here? And remember that now we can talk about what's going on with epsilon. So if the epsilon is a constant or something else. So I place a point charge Q here at the given place of, let's say, x0, and I want to find what's going on with the potential at the point of observation of P. Good? Is that clear? So, assuming that epsilon1 is a constant, so it means that it has no functionality of functionality of the coordinate x or x prime. So then what is happening, essentially, your problem will be simplified into the divergence of epsilon1 e equal to rho, and that will be divergence of e equal to rho divided by epsilon1. Okay, so I simplify d with epsilon1 e. Is what I have done. So what's that? Are you able to solve this problem? Divergence of e equal to rho divided by epsilon naught, and of course curl of e is equal to 0, which means that e is given by minus gradient of a potential. So the above expression will be simplified into minus Laplacian of phi equal to rho divided by epsilon 1. Then means that Laplacian of phi is equal to minus rho divided by epsilon 1. All right. You can use the second Gauss theorem and assuming the green function, which is 1 divided by x minus x prime, and doing the integration and assuming that this material goes to infinity, then you can solve it. The only difference that you will get with respect to vacuum is you will get 1 divided by 4 pi epsilon 1 integral of rho of x divided by x minus x prime. This is using a green theorem, E3 of x prime. So for our charge, which is a point charge, rho of x prime is q delta of x minus x0. And if you place it here, then we get phi of x equal to 1 divided by 4 pi epsilon 0. Epsilon 1 q divided by x minus x0. Nothing changed. Essentially, the only thing that is changed is replacing epsilon 0 with epsilon 1. And that was the feature of, let's say, isotropic material, epsilon 1, which is not function of the coordinate. When it's a function of the coordinate, as I say, that it should be handled appropriately. Now let's choose another problem. I have a boundary now. This is x. This is y, which I'm not showing it. And that will be z direction. Okay. I have two regions, z greater than 0, z smaller than 0. And I choose the coordinate such a way that it distinguishes two different places. One which they have dielectric constant of epsilon 1, and the other region which has the dielectric constant of epsilon 2. And of course, I assume that that goes to infinity. Okay. The same here, of course, remember also that's true. That goes to infinity. So they are touching all in that place. It is epsilon 2. I don't have any problem so far. And the only things that I know when we discuss that at the boundary, I have to be very careful. What is going on with the electric field? D2n minus D1n should be equal to sigma. Okay. Good. And E1t is equal to E2t. That was another condition that we had. That's for boundary. Now, I'm placing a point charge here at the distance of what we do have, A. Okay. I'm placing a point charge of Q at the distance of A. Now, we would like to do a little bit of mathematics and find out what is going on with the potential here and potential here. Good. Is a problem that someone can give it to us. How do you solve this problem? First of all, we should know that here, Laplacian of phi, due to the discussion, I don't want to repeat it again, these epsilon 1 and epsilon 2, they're independent of the position. So in any cases, we are dealing with Laplacian of phi equal to minus rho divided by epsilon 1 or 2 or 3 or whatever, epsilon I, okay? Which is the property of the material. Or let's write it epsilon in general, without epsilon 0. And on the z smaller than 0 or z lower than 0, there is no charge, so I'm expecting the Laplacian of phi to be 0, while the other side, Laplacian of phi should be equal to rho divided by epsilon 2. Okay? So for z greater than 0, the positive part, I'm expecting that will be a Poisson equation with a constant, a dielectric constant of epsilon 2, while for z smaller than 0, I'm expecting to solve a Laplace equation, which is a Laplacian of phi equal to 0, and that's the same phi. And I know that at the boundary, I have to follow these boundary conditions. So the logic that we may follow is very similar to what we had for a charge close to a conductive plate. Here is a change in epsilon, and we believe that there is an image charge which is showing up here at the distance of minus a, but we don't know what is the value of the charge. Okay? So for region number one, which means that the place that Laplacian of phi is equal to 0, we do have an imaginary charge. Imaginary charge of Q prime. As we just saw, what is the potential due to the both charge is 1 divided by 4 pi epsilon 0. Oh, let's say, let me take epsilon, 1 divided by 4. Then at any given place of this point, let's call it x, which is here. From the first charge, I have Q divided by epsilon 2, and the distance is between the charge, the real charge, which I call it x0, plus the Q prime divided by epsilon 1 x minus x1. Okay, agreed? Or not? When we are looking at the field, so remember that is for z smaller than 0. For z smaller than 0, I'm expecting that both of them, they have the same dielectric constant because we are solving the problem there. So we have 2 point charges. One is here, which is q. The other one is here, which is q prime, which we don't know the value. But since we are considering and finding the potential at z smaller than 0, then inside of the material of epsilon1, I'm expecting to have a potential which is given by this expression. Clear?
Sorry, this is the potential everywhere, right? For
No, for z smaller than 0.
Okay.
Okay. I'm expecting 2 different regimes. One is z greater than 0. The other regime is z greater than smaller than 0. Okay.
And you're putting epsilon1 for both of them when we are only looking at z less than 0?
Oh, let's go with this. Okay. Let's discuss that from the beginning. Maybe I have done a mistake, or maybe there is a confusion here. So we have 2 regions, z greater than 0 and z smaller than 0. All right. What is happening with z greater than 0? Laplacian of phi is equal to minus rho divided by epsilon 1. Sorry, epsilon 2. My apologies. I think that was the mistake. Okay. Epsilon 2. Okay. Is that clear? Then at this place, what do you expect? At this place. I have a charge of q, which is located at distance of a. So I have to do the mathematics and find out the distance between these two. All right, because that's what matters. So for this region, the potential at any given place of x is given by 1 divided by 4 pi epsilon 2. Is that correct? The charge, which is q, divided by x minus, I call the first charge x0. Okay, so that is the place of these, which is x0.
But then how about the contribution of the image charge?
Wait for it. Wait for it. That's the first contribution. The second contribution comes from the image charge, okay, which is what? Which is 1 divided by 4 pi epsilon 2, because we are considering inside of that material is for z greater than 0. Okay, but is given by q prime divided by x minus x1, and the x1 is that distance. Okay, that is on the z greater than 0. What is happening with the z smaller than 0? For z smaller than 0, that's the real charge of q, that's epsilon 2, that's epsilon 1, and I'm talking about this region. and I have the image charge of Q prime. Will Q prime contribute to the potential here? Yes or no? Q prime. I'm talking about Z negative. Is the Q prime a real charge? Is not a real charge. So I'm not expecting any contribution, no contribution from the image charge is expected. All right. Which material are you considering? Epsilon 1. So definitely the potential will be 1 divided by 4 pi epsilon 1. All right. Which charge will contribute to the potential here? Which one?
Q.
The Q. But now, since there is a jump from epsilon 2 to epsilon 1, I'm not expecting that the charge will be exactly Q. It may be a different one. Can be a Q second, which is given by Q second x minus x0, the same distance, which is that one.
How about the boundary condition?
We will apply that because we don't know what is Q prime, we don't know what is Q second. We have to apply the boundary condition to find those, and then we get the potentials.
But do we have the potential equal to 0 boundary condition on this
No.
So why do we consider the image charge then? Because like previously we considered the image charge to have the boundary at potential 0, right?
Yeah, the point is that we are using an approach to help us without going into deep mathematics and solving that differential equation. Okay, there is a jump there, similar to what is happening for the conductive as well. Okay, for the conductive, the same story happens. You have vacuum, or you can have a dielectric. And the other side, what you have a potential of 0. What is essentially that was the goal, that after solving these, I want to solve that for specific conditions. So I jump a step, an educational or pedagogical step, just to not tell you why I'm using the image charge. Because there is a jump there. And I know the solution for the conductive. As soon as I know the solution for the conductive, which means that epsilon goes to infinity, then I am changing the epsilon to not go to infinity, but to being a certain value, and I'm trying to find a way the solution. Indeed, if someone wants to really solve that equation, has to solve Poisson and Laplace equation with that boundary condition there. That's just a way to simplify the things. It's not the only way. So, guys, just to recall, I'm going back and telling you the story, and then I will go back to the upper side and see what is happening. So, if you have two material, epsilon 1 and epsilon 2, if we put a charge of Q here, and the distance of A. If the two materials are identical, I'm expecting the potential to be 1 divided by 4 pi epsilon 1 or epsilon t, charge divided by the distance that you are looking for. Since the charges are, the dielectrics are different, then I say, well, okay, where are you solving the problem? 2 places, either that region. If you are looking at that region, you have 2 charges. One due to the boundary changes, which I call it Q prime. And then you get the contribution here from both charge. All right. And the second scenario is that this is true for z greater than 0. If you look at the z smaller than 0, then we have a different scenario. Definitely the image charge does not exist because on the z negative, there is no net charge, but you are not expecting to see the same charges because the boundary has changed. What you see is a different charge, which we call it q second. Then what we have for z smaller than 0, we have potential of x, which is given by 1 divided by 4 pi epsilon 1, because we are talking about this region, q second divided by x minus that distance, okay, which is this one, which is a along z direction. What about the other side is for z greater than 0, we have 2 charge contribution, but we are talking about material number 2, so it will be epsilon 2 q divided by x minus x0 plus q prime x minus, or should I say plus x0, guys? Do you accept this from me without going to deep mathematics? Okay, fantastic. Not deep mathematics, simple mathematics. Okay, and then we have boundary condition. Let's first write them down in terms of a and the distance, so let's say the position of that one, which is z. I'm sorry, is x. So let's write it down. So x is given by x I hat plus z hat. x0 is given by a z hat. So x minus x0 is given by x squared plus z minus a power of 2. And that is symmetric. We know that x and y, they are identical. You can also take the derivative. You can write also y0. So if you want to really look at the two-dimensional, I have to write that expression y j hat plus z k z hat or k hat. X minus x0 is equal to square root of x squared plus y squared plus z minus a power of 2. While for x plus x0, that will be square root of x squared plus y squared plus z plus a power of 2. Okay, so for two sides of z smaller than 0, then I have phi, I call it phi negative of x is equal to 1 divided by 4 pi epsilon 1 q second divided by x squared plus y squared plus z minus a power of 2 power of 1/2. For z greater than 0, I have phi plus of x 1 divided by 4 pi epsilon 2. Then I have two terms, q divided by x squared plus y squared plus z minus a power of 2 power of 1/2 plus q second, q prime divided by x squared plus y squared plus z plus a power of 2 power of 1/2. Okay. Now we have to apply. Yes. Do you have questions, guys? Okay. So now we have to apply the boundary condition. What are the boundary conditions? Oh, let's go here. We already wrote that. Those are the two boundary conditions that we have. Good. So First boundary condition will tell us that tangent of electric field or electric fields are identical. Which means that E to T is equal to E on T. How do we find the tangent? First of all, remember the electric field is given by minus gradient of phi. Electric field in place 2 or inside of the dielectric 2 is given by minus gradient of phi plus, and electric field for the negative side or material number 1 will be given by minus gradient of phi minus. Do you agree? Good. So now we go with the continuity issue, and let's see what we will get from this continuity issue. And then we do know that E to let's say D2n is equal to D1n because there is no net charge density at the boundary. You may get a charge density due to the polarization, but there is no net charge density there. Are you following, guys? Good. Okay, perfect. Now we will go with the first one. So what are the tangents? So remember the plane was like this. So I didn't show the two-dimensional way. So this part is Z, this is X, that side is Y. And definitely normal to this plane is along Z direction, right? That's normal is Z direction. So whenever we talk about normal, we are talking about Z component of D1 and D2. What about the tangent? Along X or Y? We can consider X, we can consider Y. They are identical, nothing will gain. So when we talk about tangent, we are talking about XY component of E1 and E2. So now we will apply the first and second boundary condition associated to this. The first one will be E2x will be equal to EYX. That's from the tangent. So what does it mean? That will be minus derivative. I'm using these expressions, guys, with the potential. Minus derivative with respect to, with respect to X of E potential, E2 is negative, positive, equal to minus derivative of X of phi negative. Where? At the boundary. Where is the boundary? Any places that Y and Y is equal to 0. For example, for my case. Sorry, Y and Z. Essentially Z, but I consider also Y to be 0 for simplicity. Z equal to 0. And of course, in parentheses, I will write Y equal to 0, including Y equal to 0. Good? Perfect. That's the first boundary condition. The second one is D2n is equal to D1n. What does it mean? D is given by epsilon. 2 with a negative sign, derivative with respect to z of phi plus must be equal to minus epsilon 1 derivative with respect to z of phi negative. We're exactly at the same place. Good. Let's take the derivatives. So derivative with respect to x of phi plus. Phi plus is the above one. It will be 1 divided by 4 pi epsilon 0, epsilon 2. Q, take the derivative with respect to x, will be 1/2 goes away. Let's go with the negative sign. Minus 1/2, minus 1/2. 1/2 goes away, 2 minus goes away. It will be x divided by x squared plus a squared plus 1/2. And the other one will be the same, q prime x divided by x squared plus a squared, power of 3/2, sorry. Do you agree? Derivative with respect to x will be minus 1/2 of 2x divided by denominator power of 3 divided by 2. Since there is a minus sign here, the minus goes away. There is a coefficient of 2 which goes away with 1/2. What about the derivative with respect to x of phi minus? Phi minus had only one term, so it will be 1 divided by 4 pi epsilon 1. Taking the derivative will be identical. It will be q second x divided by x squared plus a squared power of 3/2. From this expression, boundary condition for both, what I will get q plus q prime divided by epsilon 2 is equal to q second divided by epsilon 1. These two, they should be identical at the boundary. This is what I'm doing. So all goes away, x goes away, the denominator goes away. The only part that is remaining is 1 divided by epsilon 2, the charge, 1 divided by epsilon 1, and the charge. What about the normal component, which means that we have to follow the minus epsilon 2 derivative with respect to z of phi plus equal to minus epsilon 1 derivative with respect to z of phi minus. Okay, so derivative with respect to that will be epsilon 2 phi plus will be derivative with respect to z. Derivative with respect to z will be z minus a. Yes, okay. That will be 1 divided by 4 pi epsilon 0, epsilon 2. Then we have q multiplied by z minus a divided by denominator, which is again, it can be x squared. And we are assuming z equal to 0, then that will be minus a divided by x squared plus a squared of 3 divided by 2. Then we do have the second term, which is plus q prime a divided by x squared plus a power of 2 power of 3 divided by 2. And the other side will be epsilon 1 minus goes away with the derivative. then I will get 1 divided by 4 pi epsilon 1 q second with a negative a divided by x squared plus a squared power of 3 divided by 2. So epsilon goes away from both sides. I mean, epsilon 2 goes away from this side, epsilon 1 goes away from this side. The a divided by x2 minus x2 plus a squared power of 3 divided by 2 goes away. Then you will get minus q plus q prime is equal to minus q second. So it means that we will end up with two equations, which q plus q prime is equal to epsilon 2 divided by epsilon 1 q second, q minus q prime is equal to q second. Good. Okay. So sum them up together. Q second will be 1 plus epsilon 2 divided by epsilon 1. The other side you will get 2q. Therefore, q second will be 2 epsilon 1 divided by epsilon 1 plus epsilon 2 q. And substituting it into this expression, q prime goes there, q second will be here, then it will be epsilon 1 plus epsilon 2 minus epsilon 1. That will be, let me just check for the sign, if I'm not mistaken, q prime will be, okay, that will be epsilon 1 minus, sorry. Epsilon 2 minus epsilon 1 divided by epsilon 2 plus epsilon 1 of q. So we got both expression for q and q prime. Let's substitute it here. Let me just memorize them. Okay. For Z negative, potential will be 1 divided by 4 pi epsilon 1. Then I have q second, which q second will be 2 epsilon 1 divided by epsilon 1, epsilon 2 plus epsilon 1 of q. Then we had 1 divided by x squared plus y squared. I'll put it as r square. Is that fine? It's just cylindrical symmetry, because I know that this has cylindrical symmetry. So I'll put it as a r square plus z minus z plus a power of 2 power of 1 half. Oh, sorry. Minus. Good. Just I substituted in the expression. What is happening with z greater than 0? Then I have the potential. Let's call it this was phi minus, that was phi plus. Was 1 divided by 4 pi epsilon 2. Then we had two contributions. One with q, which is z minus a. So it will be q divided by r squared plus z minus a power of 2 power of 1/2. And the other one was plus epsilon 2 minus epsilon 1 divided by epsilon 2 plus epsilon 1 q divided by r squared plus z minus plus a power of 2 power of 1/2. Do you agree? Okay. And you can check that on the boundary, that should be identical. What is happening with the boundary? Wait, what happened with the boundary or at the boundary? Which means that z is equal to 0, or z goes to be 0. So definitely the potential should be identical. You will see that if you tend to phi minus when z goes to be 0, that should be 1 divided by 4 pi epsilon 1 to epsilon 1 divided by epsilon 2 plus epsilon 1 q. Then that will be 1 divided by r squared plus a power of 2 of 1/2. For the other one, phi negative plus z goes to be 0. It will be 1 divided by 4 pi epsilon 2. And then the denominator will be identical for both of them. So it will be 1 divided by r squared plus a squared power of 1/2. Then I do have 1. And from the other one, I have epsilon 2 minus epsilon 1 divided by epsilon 2 plus epsilon 1. If you sum them up, you will get 2 epsilon 2 divided by epsilon 2 plus epsilon 1 q, which they're completely identical. You will see that the potential is fine. So you can take the derivative, and from, as we say, that from the derivative, you can get electric field. Electric field at place of 1 or material 1 number 1 or material number 2. I could do that with mathematics and just plotting it for you, but you can do it by yourself as well, if you wish. And we can go to several different cases. So this material number 2, this material number 1. So what happens if material number 1 is equal to material number 2? Then what we are expecting for the electric field to be continuous here. So I'm not getting any surprising fact for the charge, which is, I assume that the charge is positive if you place it here. If the two dielectrics are identical, I'm not getting any surprising effects here. However, if the dielectric is, one of them is positive with respect to the other one, or it's greater than the other one, so there will be several different scenarios. One will be like that. So here is bended negatively, guys. Or for the other scenario, if you have the charge here, so if you look at the field, it seems that outside, which is Z negative, always for all cases, you will see like a point charge. It seems that those are coming from a certain point. Okay, so that was the reason that we assumed it. And other scenario that we may consider is that we may consider that epsilon1 is tending to be infinity. So it goes to be infinite. And that is for the conductive plane. So if you assume that epsilon1 goes to be infinity, then you can look at the expressions that you have it for electric field and see what is going on with the potential in the negative sign and also in the positive sign. And you will see that if you tend epsilon to be going to be infinitely large, then you will get different expressions. For example, for negative side, definitely that will be 0, the potential, which agrees with what we assumed previously, okay, with the image charge techniques. Any points, any concerns, guys? No, I will ask you a puzzle. Definitely at the boundary, there will be a polarization appearing. What is the charge density there due to the polarization?
Sorry, can you repeat the question?
So at the boundary, right? So at the boundary, we do have different Ds, right? At these places. We have D2 and we have D1. All right. Can you tell me what is the charge densities due to the polarization? Due to the P, what is the charge density here? Of course, the net charge is 0 as we use that fact and we measure what is going on with D2 and D2n and D1n, but however, there is a polarization there. So how do you calculate that? You are muted.
So are we no longer considering that there's a point charge only on one side? I think I'm confused about the problem setup.
Oh, you place a charge here, which is what we did, right? And then we have epsilon2 and epsilon1, right? So the materials are different. Definitely, I'm expecting a charge distribution to be appearing on the surface. What are those charge distribution? They are not net charges. They are coming from the existence of material.
So don't I just take the normal of the electric field?
Normal
or subtraction or the difference between the normal of this electric field to get the charge
E2n
density?
minus E1n?
Yes.
How come?
Over epsilon, not sure about much epsilon.
Yeah, that's a point. That's a point. So definitely, you know that epsilon2 E2n minus epsilon1 E1n is equal to 0. That is what we use. Okay, that is very clear. Definitely, the surface charge density is given by P dot N. If we discuss, do you remember we discussed that? We say that that's given by sigma. The point is that to find what is P.
Can we find it from the displacement and the electric field? Like P
Exactly.
was
Exactly.
like a constant times electric field, right? So,
Yeah, you have to find it from what also Edith mentioned. So going with the displacement vector, from the displacement vector, you can find P's. And when you can find P for material number 1, you can find P for material number 2. And then you can look at the difference between the two and see what is the charge densities. So in any cases, if you do a little bit of mathematics, you will see that the charge density is proportional to epsilon2 minus epsilon1 divided by epsilon2 minus epsilon1. I don't hear you.
sorry, has it like it should be probably one of them it has to be plus. Oh yeah, okay.
Is that clear, guys? So I have 2 places, one place here, which is, let's say, is plastic, a kind of plastic, epoxy plastic. This side is a glass. Then I put a charge here, and we just did the mathematics. We find out what's going on with the electric field and potential. And since the material is changing, I'm expecting a certain charge distribution appears on the surface due to the polarization, due to the fact that we do have different materials. Okay, perfect. So any question? Shall we go with the last problem, which is a little bit difficult? Good. Now we change the geometry. I have an electric field, uniform electric field, and then I place a sphere here. Oh, let me do that. With a radius of A and with a dielectric constant of epsilon. Let me be clear. What's going on with electric field inside? What's going on with electric field outside? Due to the fact that it is a dielectric with a dielectric constant of epsilon, I'm expecting a certain charge distribution appears on the surface of the sphere. Okay. What is the charge distribution? On the surface. Clear question? A sphere with a dielectric constant of epsilon with a radius of A, we are placing in an external electric field of E0, which is a constant value along specific axis, which for simplicity you can consider that's the z-axis. And then I'm asking you what is going on with electric field inside, electric field outside, and what is the charge density at the surface of the sphere, on the surface of the sphere. I will pause the video. I'll give you 10 minutes to solve this. Perfect. So you all almost got the path to resolve this problem. So we do have 2 different regions again. One is that or let's call it R, excuse me, R greater than A, which, excuse me, we have Laplacian of phi equal to 0. I call it phi in, and we have R, sorry, that was R smaller than A, R greater than A, which Laplacian of phi in principle is not 0 because we know what's happening. I'm assuming also the infinity when the place is, the field is created, which I have phi out, okay? So this, as we briefly mentioned, so let's consider that that's a z-axis. Then the system is symmetric around about z. So it means that there is no independency. In principle, if you solve the problem, then the potential everywhere will be given by summation. I think, if I'm not mistaken, was 1 divided by epsilon 0 or epsilon in general for the symmetry. It was summation of L, summation of M, which is changing from minus L to L. That was changing from 0 to infinity. Then we do have 1 divided by 2L plus 1, if I'm not mistaken. Then we had 1 divided by R power of L plus 1, YLM theta and phi. Okay, I think it was something like that, which for our case, since is holding cylindrical symmetry, we simplify this and we are not using expansion on phi. Then simply what we will get the potential should be function of 1 divided by 4 pi, and then we will talk about the epsilon, which epsilon should be placed there. Take away the phi, it was summation of AL R power of L plus BL R power of L plus 1, and then we have PL of cosine of theta, which is L is changing from 0 to infinity. So we are expanding in this term. Okay, so remember that there is no e power of I and phi due to the fact that this is holding a cylindrical symmetry. So I'm not doing the YLM expansions. I'm doing simply in terms of Legendre polynomial. So we do have two different regions. One is R greater than A, and one region is R smaller than A. R smaller than A, which means that also includes R equal to 0, then R power, 1 divided by R power of L plus 1 will be singular. So for phi in, the only term that plays role will be R power of L, PL of cosine of theta. That's the only term that plays role. For R greater than A, which also R can go to infinity, phi out will have the following contribution, which is L from 0 to infinity. In general, we do have both terms, so I will call them BL R power of L plus CL R power of L plus 1, PL of cosine of theta. Now we have to learn about the boundary condition. What is happening with the boundary condition? How many boundary conditions do we have for this sphere? The first one is that at r going to infinity, we have to recover the field, or we have to recover the original potential that we had. What was the field look like? I say that the field is uniform of E0 along the z direction. So field was E0 along z direction. What is the potential associated with this field? Minus E0 z. All right, because that's the potential at r going to infinity. Because if you take minus derivative with respect to z of phi, then you will recover the electric field. So essentially, electric field is given by minus gradient of phi. If phi is given by minus E0 z, then that will be E0 z hat, which is what we started with. Or essentially, you can take just the integral and then finding the potential from the electric field. Fantastic. So I know that for infinity, the electric field outside is given by, as the potential outside is given by minus E0 z. What is the z in the Cartesian in cylindrical coordinate? Is minus E0 r cosine of theta. Okay, so at r tend to infinity, the potential tends to be minus E0 r cosine of theta, which cosine of theta essentially is P1 of cosine of theta. Therefore, BL with L equal to 1 exist. Okay, so it means that B1 is equal to minus E0 and B0 essentially is a constant, just forget that. BL not equal to 1 is 0. All right. Good. Now then, you have a question. I see that.
Sorry, I'm not sure why we're having a contribution of R to L outside the sphere. I mean,
because I see that the potential is given by E0 r cosine of theta. I have r power of 1.
Okay. Yeah.
Okay.
Thank you.
Of course. So therefore, for phi in, still I have the summation of L equal to 0 to infinity, AL r power of L PL cosine of theta. But for phi out, what I do have now, I have B1 r P1 cosine of theta plus the summation of L from 0 to infinity of CL, excuse me, L plus 1 PL of cosine of theta. Remember that B1 also is given by this expression. V1 is simply minus E0. Any question so far? So far, so good, right? Now let's look at the boundary that we do have. So that was the sphere that we had. The radius was A. The dielectric was epsilon. Outside was epsilon 0, because it was vacuum. Then at the surface, or on the surface, what do you have as a boundary condition? The tangent should be identical. Tangent of electric field should be identical. And normal should be given by the charge density, which normal is, we are talking about normal of displacement vector. So D2n, or let's write it in this way, D outside n equal to D inside n. What does it mean? How do we define the normal to the surface? Normal to the surface is r hat, and then we are translating these in terms of r hat, the outside in terms of r hat is equal to d in terms of r hat, or just simply writing dot r hat. Clear? That's along the normal to the surface. And you can calculate what is the D from potential. D essentially is given by minus gradient of the potential. All right. With the proper coefficient, of course, with epsilon at the front. And if you do the expansion, that will be minus epsilon. Gradient, you have 3 terms. One of them is r hat, which is shows up with derivative with respect to r, and the other they will be in terms of theta hat and phi hat. Those are orthogonal to r hat, so the only term that remains, it will be minus epsilon 0 derivative with respect to r of phi out is equal to minus epsilon 1 derivative with respect to r of phi in. Or it was, I think we assumed that is phi. Okay, is that correct? Melika, you have a question? Okay. So therefore, we do have minus epsilon 0 derivative with respect to r of phi out is equal to minus epsilon derivative with respect to r phi in. And from the tangent, E tangent, it will be E outside tangent, and is equal to E inside tangent. That will give us, for example, derivative with respect to theta or derivative with respect to phi will be the proper tangent one. I will assume that only the theta one. So that will be minus derivative with respect to theta of phi out is equal to minus derivative with respect to theta of phi. You can take these expressions and you can find out what's going on with, I mean, simply you can do the mathematics and using the relationship that PLs, they are orthogonal to each other, okay? And then from those expressions, I'm just using the calculation in your book. So we will find that phi in is given by minus 3 divided by epsilon divided by epsilon 0 plus 2 E0r cosine of theta, and phi out is given by minus E0r cosine of theta plus epsilon divided by epsilon 0 minus 1 divided by epsilon 0 plus 2 of E0 a power of 3 divided by r power of 2 cosine of theta. So, by the way, this is a simple calculation. If you do that, then you will get a relation between A1, B1, and C1, and then you will have to find those relationship, which is very similar to what we have done previously for plane. Okay, good. So now we got the potential, and the potential is a little bit interesting. If you look at that expression, is fantastic. So the first conclusion that I will get is that this term, I mean, let's calculate the electric field. Let's do the mathematics and find the electric field. Electric field inside. What I have to do, I have to take the derivative of this with the negative sign, right? Since this is only function of r and theta, definitely you will see that the relation will be given in terms of theta and r, okay? But it will be along the z direction. So I can write that in the terms of that's z in the Cartesian coordinate. That will be also z in the Cartesian coordinate because it's r cosine of theta. And that one, if I'm that one gets a little bit more complicated, but E in is given by 3 divided by epsilon 0 plus 2 of E0 z hat. So whatever happens, what material it will be, the E inside of this will be along the z direction. Okay? Doesn't matter what is epsilon. Whatever epsilon is, it seems that outside field will be imprinted inside of the material. Okay? The same story happens with outside. If you look at the E outside, you have two terms. One term, the first one, again, is minus E0 z hat. But the other one, it will be given by a coefficient, of course, I mean, which is related to what we know. Then you do have also two terms, which is 1 divided by r squared of z hat, some coefficient, with another one which is given by the derivative with respect to r of, there will be an r hat, essentially. There will be a term which is proportional to r hat. Okay, so it tells us that even outside, for the far distances, again, that is given along the z direction. But when you are close to the sphere, when you are coming here for r small, then there is a component that appears here, which is normal to the surface. So it seems that normal to the surface plays role here in the near field, and you will see that the electric field is always, of course, normal to that region. But for the far distances, only is given by E minus E0, and plus E0 z hat. Is that clear? So without the sphere, without that sphere, what is the contribution of the electric field? Is that term only playing a role? Now, if you place the sphere inside, that second term appears in the calculation of the potential and also in the calculation of the electric field. So this is due to the polarization, which is induced by external electric field. Okay? And even from these, you can calculate what's going on with the charge density on the surface. Okay? So I think I will not keep you for a longer time. I will stop here. So do the last part by yourself at home. So just try to calculate what's going on with the charge density at the surface. There are a lot of other problems similar to this one. For example, you can have a material with the charge density, with the dielectric of epsilon. You make a spherical hole inside, and you want to understand what's going on with the electric field inside of that. Or many different scenarios. You may have a plane dielectric with a half hemisphere bump, and then you have two different regions, or you may have three different regions, and someone may ask you what is happening with the charge distribution there. So try to understand better the physics behind of these, and a little bit of solving a little bit of different problems and challenging yourself. Okay, so I will see you next week with magnetic field, which now I think everything is done with electrostatic and materials, and then we will go with the magnetic field and learning about magnetic field and magnetization as well. And finally, the last two lectures will be about gauges and Maxwell equations. So I will stop the video.